Ferro and Berto, and with the BDP foundry, that is a cast iron foundry in the north of Italy. The aim of this work is to evaluate the effect of the in-mould inoculant composition on microstructure and fatigue behavior of heavy section ductile iron castings. In literature, there are few works focused on the characterization of the fatigue behavior of perlitic ductile iron castings. This work may be helpful to expand the limited available data. In this work, heavy section castings with different inoculation treatments were considered, and the specimen for tensile and fatigue tests were taken from the last to solidify zone. The obtained results showed that an optimization of the inoculation treatment optimized the microstructure and the fatigue behavior of heavy section perlitic ductile iron castings. The castings we produced were blocks with a section of 300 millimeters per 250 millimeters, 300 millimeters in 8, with feeders on the top surface. Such dimensions were chosen in order to increase the solidification times, that was about 3 hours. The mold contained 4 of each blocks and was made in 4 sand. The castings has a common gating system that to have a uniform conditions of occurring. The material that was used was a perlitic ductile iron casting, ductile iron, which final composition is reported in this table. 2 castings, named A and B, were produced with these chemical composition and with different inoculation treatment. The first castings, named A, was inoculated with inoculants containing silicon, aluminium, and calcium, while the second casting was inoculated with inoculants that contain also red earth and bismuth. In order to evaluate the mechanical properties of the material, a cast sample was casted according to the European standard, and specimens for the tensile tests were taken from the red zone in the figure. It can be noted that the results of the tensile test meet the requirement of a perlitic ductile iron. In order to evaluate the mechanical properties of the castings, specimens were taken from the elastic to solidify zone, as represented in the figure. It can be observed that the mechanical properties of specimens from the castings are lower with respect to those of the separated cast sample. It is obvious because there is those specimens were taken from the last to solidify zone. There are also some differences in ultimate tensile stress and elevation and failure between the 2 castings. Micrographs, in order to evaluate the microstructure of the material, micrographs were taken according to the American standard. Here we have some definitions of the parameter that was evaluated. The shape factor, that is the ratio between the area of each graphite particle and the area of the reference cycle. A graphite particle is classified as a graphite nodule if this shape factor is greater than 0.5. The percentage nodularity is the ratio between the number of the graphite nodules and the number of all graphite particles present in the casting. The nodule count is the number of graphite nodules per square millimeters. The results of the micrographs taken for casting A and casting B are shown in this table. We can see that the nodularity and the nodule count is greater for casting B than casting A, while the mean nodule diameter is lower. From the etched conditions, we can see that the matrix is perlitic, with some percentage of ferrite at grain boundaries and surrounding the graphite nodules. This ferrite was found slightly higher in the case of casting B that was inoculated with bismuth. Small amount of degenerated graphite was found in casting B, inoculated with bismuth and rail arc. The formation of such degenerated graphite shape is attributed in literature to the presence in melt of great amount of detrimental elements such as lead, antimony, and bismuth that was used for casting B. So the presence of degenerated graphite is suggested to have detrimental effects on the ultimate tensile stress and on elongation and failure, but without decreasing the yield stress that is similar. These conditions is also found when in the case of chunky graphite. That is, there are many works that in literature on the effect of chunky graphite on the tensile results. Axial fatigue tests were conducted at room temperature with a load ratio equal to 0 on specimens that were taken from the same zone of the tensile test specimen. All the results have been evaluated, statistically elaborated using a log normal distribution, and the Euler diagram is plotted. We can observe that the stress amplitude at 2 million cycles for casting A is equal to 120 megapascal, with a scatter index that is equal to 1.5. In the case of casting B, there is an higher values of the stress amplitude at 2 million cycles and a survival probability of 50%, with a narrow scatter band and a lower scatter index equal to 1.1. Fractals of phase were evaluated using a scanning electron microscope, and in order to evaluate the crack initiation site. For all the specimen, shrinkage porosities act as crack initiation site, and it can be seen in these figures that for casting A, the shrinkage porosity are greater than casting B. This could be attributed to a better inoculation treatment that induces the higher nodule count. So we have a greater graphite expansion that reduces the shrinkage porosities. The cracks propagate in the propagation zone around graphite nodules, while final failure happens in a Brinell manner by cleavage for all the specimens that were observed. So, in conclusion, we can conclude that the in-mold inoculation treatment affects the metallurgical parameters and mechanical properties of heavy section perlitic data alarm castings. The inoculant containing bismuth and rare earths increase the nodule count and reduce the dimension of the shrinkage cavities, increase the fatigue limit and reduce the fatigue scatter band. But they could cause the formation of the degenerated graphite particles that has negative effect on the ultimate tensile stress and elongation and failure, without decreasing the yield stress. The fractography showed that the microshrinkages close to the specimen surfaces act as a crack initiation point from which the fatigue fracture propagates around the graphite nodules, while the final failure happens in a Brinell manner by cleavage. In conclusion, shrinkless cavities are suggested to have higher influence on the fatigue resistance with respect to the degenerated graphite particles, in this case of heavy section perlitic data iron castings. So I finished my presentation. Thank you for your attention.